Anyway, so maybe I will start with the introduction, which is a pleasure for me to introduce you, Hugues Chaté. He's an old friend and collaborator of us. He's a senior scientist at CEA in Saclay, France. And he obtained a PhD from the University Pierre and Marie Curie in Paris under the supervision of Paul Manneville, if I am right, working on spatiotemporal intermittency and related topics in nonlinear dynamics. And after a short postdoctoral stay in Bell Lab in the States, he joined back the condensed matter physics department in Saclay, and essentially has developed most of his career there. His career covers an amazing range of topics, from nonlinear dynamics to essentially everything on statistical physics, critical phenomena, active matter, etc. His most recent activities are on collective motion and active matter, fields in which he has made countless pioneering and breakthrough contributions. So he's a world leader on all these things. In particular, he was a leader of an advanced study group on the statistical physics of collective motion at the Max Planck Institute in Dresden. And he has served on the board for Physical Review E, and is now presently editor of Physical Review Letters, has been for some years now. So please, Hugues, we are all yours.
Thank you for the nice words. I'm the lead editor at Physical Review Letters, which means I'm not an editor. You know, it's too complicated to get me started on this, but
I get confused.
Those of you who are interested can write to me. Anyway, so this title page is supposed to be moving. Yes, I hope everybody sees it moving. And if I don't go over time, you will know what this is about, the background, the moving background at the end of the talk. And so mostly I'll be reporting on work done by Benoît Mao, who appears on the top right here. And this is based also on previous work, notably with these people listed here. So I will go back to very general things, and in particular, what happened in 1995, following the work of our next speaker in particular. And so most of you, I guess, know that long-range orientational order from a spontaneously broken continuous symmetry is impossible in equilibrium two-dimensional systems. That's the famous Mermin-Wagner theorem. And an example of that is the XY model, which I don't define here. So either you know it or you don't, but it doesn't really matter. But either the XY model with either ferromagnetic alignment of spins or nematic alignment of spins gives the same phenomenology. There is a low temperature quasi-ordered phase where correlations of the spins decay algebraically in space and time with continuously varying exponents. And there's a famous BKT, Berezinski-Kosterlitz-Farless transition limiting this quasi-ordered phase, and the phenomena ruling that transitions are the binding and unbinding of defect pairs. And we'll see some illustrations of this in the context of active matter in this talk. But so in 1995, Vicsek and collaborators implicitly showed long-range order, not quasi-long-range order, in the two-dimensional model, minimal model for collective motion, which is now called the Vicsek model. And I will, of course, show you what it does later. At the same time, actually slightly just after that, Toner and Yuhai Tu directly showed by calculation that indeed true long-range order is possible in 2D based on a hydrodynamic theory for that Vicsek model. And I will see details about this. So already in there, you know, it was, to me at least, the first striking evidence that active matter, as it is now called, can exhibit important properties not possible in equilibrium settings. And since then, many such impossible properties in equilibrium have been uncovered in active matter, of course. Okay, so 1995, the Vicsek model. I will not show you in original graphs. I just defined the model here by words, which I keep thinking is a better way. because it doesn't matter how you really implement the details. So here we're talking about point particle moving in a 2D for this talk, two-dimensional space of lattice, no lattice, but you can also work lattice versions. In the original version, they move at discrete time steps, and they have constant speeds or constant displacement from time step to time step. And they don't carry an intrinsic physical polarity like a physical active particle would, but this is just given here, given that they are point particles, is given by the velocity. So that's another simplifying option compared to any physical active particle you can think of, but it doesn't matter so much. And now the only interaction is a local ferromagnetic alignment within distance 1, say. By this, I mean here just the local sum of the velocities or polarities, it's the same thing, of anybody within distance 1 of yourself, including yourself. And that is in competition with noise. So below you see two snapshots, and to the left, this is what happens when you have a low density of particles or very strong noise, or both, in a box with finite boundary conditions, which are convenient for collective motion. And you see that the noise is strong enough to destroy any alignment, persistent alignment between particles, and they are basically behaving like random persistent random walkers. Now on the right-hand side, you have the same system at a higher density. It could be the same system at a weaker noise, but here it's a higher density, as you can see. And the particles have spontaneously chosen, at least at this instant of time, to go downwards, most of them, mostly downward. This global spontaneously chosen direction wanders in time, of course, in a finite system. But here, this is collective motion as a spontaneously broken continuous symmetry in some sort of minimal setting. It's very hard to simplify the Vicsek model further. Okay, so that in 1995, Vicsek showed this and studied the transition, and based on the numerics he did at the time, concluded to a continuous direct transition from the disorder to the right to the order on the right-hand side here, to the left. Okay, order disorder transition with a second order type critical point based on numerics. Now, at the same time or just after, John Toner and Yuhai Tu, inspired by Vicsek, wrote down fluctuating hydrodynamic theory, which is, I think that's a cut and paste from one of their papers, in terms of a conserved density field advected by a velocity field. That's the second equation, that's an exact equation. And an equation for a velocity field which looks like Navier-Stokes equation, except that alignment is not preserving momentum, so you have more terms allowed because of less symmetries, and you have all terms here possible with, in particular, the first three, 2 V's and 1 grad, okay, including the usual Navier-Stokes term, but with an arbitrary coefficient. And this here, V minus V cube, Ginsburg-Landau, 5-4 potential type term, which guarantees that if alpha is positive, in particular, there is a mean value for modulus of V that arises from this dynamics. The pressure term is a compressible system, so pressures are important. It's anisotropic, and diffusion is also anisotropic, and some ad hoc additive noise term put here. So what they did at the time is there is a fairly obvious, as I said, homogeneous ordered solution in which modulus squared of V is equal to alpha over beta in some arbitrary direction. And they studied using RG, so-called dynamic RG, the stability of this ordered homogeneous collectively moving phase, two fluctuations. Okay, and they concluded at the time to the existence indeed of true long-range order, even in 2 dimensions, in dimensions 2 and 3. Hypercritical dimension is 4, as usual for these problems. And that was a calculation at the time presented to be valid at all orders in perturbation theory. So, and also predicted, maybe most importantly, the general framework of the scaling for these correlations of space-time fluctuations, which I will describe a bit later. And okay, so that's basically a very fast summary of what happened in '95 and the following years. Now, since then, there's been a lot of progress, and this is one way I've been using the last few years to represent active matter as a domain of, as a field, subfield of statistical physics, at least. And here on the 3 dimensions of this cube, which could be more than 3-dimensional, in fact, I've put down the main directions, tensions of it people have been working on. So you have here a dense to dilute kind of axis. So if you're very dense, you can have active glasses and things like that. You have something representing the dominant interaction, and among the most commonly studied, which are alignment, like I just said for the Vicsek model, and repulsion or steric interactions between particle here. And here you have this wet to dry case. In the Vicsek model, the fluid surrounding the moving particles is totally ignored. This can be a legitimate approximation for, especially in 2D, for particles walking on a substrate, and where the fluid displaced by these particles still has no influence on their walk, but is indeed a limiting factor here. So where are Vicsek, Toner, and Tu in here? They are here in this corner. So if you want this dry, aligning, dilute, active matter, DADAM is a limit of a limit case. So you would say, okay, what's the point? It's maybe not so important. So it has historical importance, as I just said, but I still believe that these days that it has more than that. And because if you want to understand anything that's going on here, except on some other limit cases, you better understand what is going on in this limit of limits here, which is, and there are still important unanswered questions there. So another limit of where the theory in particular is most developed is here at along this blue line. This is for active Brownian particles interacting strictly by repulsion, pairwise repulsion, and giving rise in particular to a famous motility-induced phase separation, which was underlying most or a lot of Mike Cate's talk this week. Okay, so we are going to concentrate on this little corner of even a higher dimensional cube of active matter studies, which keeps growing in time. Okay. Not only that, I'm going to restrict myself further to Vicsek style models in 2D, where basically, again, polarity is velocity given by just the velocity of particles. So again, point particles, constant speed, polarity equals velocity, local alignment versus noise. Now you can have, for example, a polar motion, like in so-called polar motion, like in the Vicsek model, where particles go at a constant speed and never reverse their velocities spontaneously, by themselves. You could also consider apolar motion, where a particle moves, but they have a finite rate of velocity reversal. So they basically go back and forth at some finite rate. Okay, that's called here apolar motion. And you can consider ferromagnetic alignment, which is just the sum of velocities, however the incoming angle is here, versus nematic alignment, where, to put it simply, if you have an incoming angle between two particles that is acute, these particles will align. But if this incoming angle is obtuse, then they will anti-align. That's one way of defining nematic alignment. For those of you who like formulas, instead of having sine of a difference of angle, you have sine of twice the difference between the angles of the two particles in a continuous time description. Okay, so 2 by 2, normally that should define 4 classes. One in the Vicsek context, where really there's no polarity, does not make much sense because order can never arise. orientational order can never arise. This is the case of apolar motion and ferromagnetic alignment. This case, because the particles reverse their velocities and they align these velocities locally, even locally, orientational order cannot arise. It's just completely dominated by noisy phase, discrete phase. So you're left with three phases, three interesting phases, which I call Vicsek or polar phase. This is, the polar motion and the ferromagnetic alignment that I talked about for the Vicsek model, of course. You have a active nematics, Vicsek style active nematics phase where particles reverse their velocities at some rate, fast, finite rate, and the interaction is nematic. So this is a dry version of the wet active nematics that Julia Yeomans has been talking about this week. And there's a third case where you have polar particles, so moving steadily, not reversing their velocity, aligning nematically, which is a Vicsek style mimicry of two elongated particles coming into contact. They will anti-align if they come at some obtuse angle with respect to each other. So I call this rods. The rods case, this should not be understood as actual, explicitly rod-like shaped particles interacting, but this is the closest thing that can come to be close to rods for this Vicsek, very restricted Vicsek setting. So we have three classes a priori, and one question that I will tackle in this talk is whether there are really three classes or not, which has been a long-standing question for reasons that I will explain next. So the program is really to focus on long-range order in DADAM, diluted dry aligning diluted active matter. And first I give you a little bit of state of the art. So in 1995, the problem was presented, at least by Vicsek, as an order-disorder transition, and indeed it concluded, like in magnetic systems, to a continuous transition and all that, implicitly assuming that the transition was to an ordered phase. It's actually not explicit in the paper there, but anyway. And it took a long time to realize that this is not the right way of looking at this problem. The best way to do this is to look at it as a liquid gas phase separation. So I will describe what I mean by that just later. And this was actually first shown for the activizing model is a simpler model than the Vicsek model, but one in which you break rotational invariance. So you could argue it's not really in the same class at all, by Alexandre Solon and Julien Tailleur. So, but then that phase separation scenario carries over to the case of Vicsek and others, and other DADAM systems, all of them that I mentioned here at least. Now, the physical mechanism for this phase separation, which I will illustrate in a minute, is a feedback between local density and local order. These are highly compressible fluids, and in the Toner 2 equation, which are written here in a sort of somewhat simpler version, the key ingredient really for that phase separation thing at the theoretical level is the fact that the linear term of here is the momentum equation, or velocity field equation, if you want, depends on the local density, which is here. Okay. If you have this in your description, then you are sure to see phase separation again, as I will show it in a minute. If you don't have this as it is here, a deterministic continuous description of a problem, then fluctuations, if you add noise and you consider fluctuations, the dressed version of this equation will introduce, even if it's not there at the bare level, will introduce a variation of this coefficient, dependence of this coefficient on the local density. And you can see this in this recent PRL paper by David Martin and a bunch of interesting authors. Okay, again, generally speaking, before I show you a specific example, so the typical phase diagram, simple phase, important parameters here are the global density of particles in your system, in your box, and the variance of the noise. Okay, if the noise is high, whatever the density, you're going to get a microscopic disordered gas. if the noise is low enough and all the density is large enough, you're going to get the ordered collectively moving in the case of Vicsek phase that I showed before. But in between, generically again, there is a coexistence phase, which can be even bigger than in this schematic diagram here, in which, in some sense, regions, patches of the liquid, of the dense and ordered patches, coexist with a residual gas. Okay. Now, this is a classic phase separation phase diagram, except that usually in equilibrium, you would expect this to be temperature, density, and a parabola shape, and a critical point on top of a parabola. Here, for symmetry reasons, so to speak, the critical point is sent to infinite density, because you cannot go continuously from the disordered gas to the orientationally ordered liquid. And that's my way of understanding it, at least. Okay. So this very schematic thing is true for all these Vicsek models I briefly described and other kinds of microscopic models. It's also true at hydrodynamic level for the various hydrodynamic theories that we and others have derived for these systems. It's also true at the kinetic level when you look, for example, at Boltzmann equation. So this is a very robust feature. So the transition is not direct from disorder to order, but it goes via a coexistence phase. Now, for the Vicsek model, I show you these two snapshots before. In fact, what happens in between is something like this. Whoops, sorry. Where you see that the particles in this relatively small system have spontaneously decided to form a traveling band with a very dense front, moving from left to right here, and a not so dense tail, but moving in a residual gas. They catch up particles when these bands catch up particles when they move, and they leave behind some particles, of course, and in a steady state, these things is moving. If you are in the moving frame of this object, everything is perfectly steady. Now, in a very large system, or a much larger system at least, here you see coarse-grained density fields. So there are so many particles that you cannot see them one by one, whereas here you can almost see it. Here you have 1 million particles, or something like this, and this is not really a movie, it's a succession of snapshots, hence the stroboscopic effects, and should run, but it's not running. Okay, good, wow. Let me see whether I can repair this. Yes, it is. So you see the bands have formed already at the first snapshots a little bit, but now they're regularized, and on very long time scales, millions of time steps typically, after some compression modes have dampened completely, you're left with a fairly regular smectic arrangement, smectic A arrangement of traveling bands. And this is already a phase with long-range orientational order, because most particles are traveling here from left to right again. Okay, so that's the coexistence phase for the Vicsek model. All right, now I will go back now to the liquid phase. So the homogeneous ordered liquid phase is in the three classes of DADAM systems that I described. But before doing this, I decided to introduce a few slides about defects. In all this literature since 1995, there is almost nothing about the role of defects in this long-range orientational order, in particular of the Toner 2 equation or the Vicsek model. Now I'm trying to show you why it's not so important to worry about defects here. So Julia Yeomans reminded us that, you know, in the continuous order field in 2D, you have topologically constrained point defects for velocity field or for a complex field. And these things, she argued, play actually a very important role in at least some active systems. Okay, so what about these defects in dry, aligning, dilute active matter, DADAM? Okay, so in equilibrium, as I said, you know, the defect unbinding rules the order-disorder transition, the XY model. In DADAM, the stable homogeneous ordered phase is possible. So normally, you know, fluctuations could nucleate a pair of defects. You almost never see it. And rather than waiting for this to happen, we looked at what happens if you are, you take a system deep in the ordered phase, so dense, relatively weak noise, everybody, for the Vicsek case, for example, everybody moving nicely together, more or less. And we constructed an initial condition, which you can see here on the right-hand side. This is colored by the mean local orientation of particles. So basically, most particles are going from left to right again. And here we have introduced, I won't tell you how, but that's not so hard to do. We have introduced a pair of defects, a positive defect here, meaning if I go around this point, the orientation of particles will turn by 2 pi. And whereas here, if I go around this point in the trigonometric direction, the orientation of particles will go by minus 2 pi. So +1 defect here and a -1 defect here for the Vicsek model. Then this is an initial condition. The parameters are those initially used to generate this fluctuating but well-ordered collectively moving phase. And we run this for short times. And here is what you see. Okay, I will run it a few times. On the left, you will see the density field. And if you look carefully, there is a big blue growing region, which corresponds on the right-hand side. I'm going to run it again. On the right-hand side to a dark region where actually order cannot even be defined because there are no particles, or almost no particles. So what you see here, and eventually the system repairs itself. What you see here is that the plus defect evolves around the plus defect, grows, the initial position of the plus defect grows a quasi-empty disordered disk, which in this case grows like time, really, its radius grows like time. Whereas the minus defects reorients the flow, and is quickly catched by this growing empty disk. And eventually order is recovered. So so that also happens in the Toner 2 equations. So basically the same initial condition, and you see also void growing, and then the system repairs itself. Basically, it happens the same way. So, and the same basic phenomenology occurs for the other DADAM classes, the active nematics, or the rod space, etc. So defects lose their pointwise character and recombine deterministically. And so this is very different from what you can think of in equilibrium XY model or something like that. And this allows, in my opinion, for these very stable long-range ordered phases. Okay, now that defects are understood, so to speak, so they don't really pollute the system for very long if they were to happen spontaneously. We can go back to a quantitative assessment of the Toner and Yuhai Tu theory. In 2012, John Toner, this was actually at the time of his advanced study group in Dresden. John Toner was a member of the group, and we realized he had a very, very bad night, I remember. Then he realized that the original calculation of 95 was actually missed or neglected a bunch of important vertices, equally dangerous, equally important as the one that was studied and led to this calculation. So the results of the 95 papers were not exact anymore. And in fact, they are still not exact anymore. So nevertheless, it is still argued in a 2012 paper that the true long-range polar order result holds. And we can come back to this later. But anyway, it was time for a numerical check of what are the exponents ruling the scaling of fluctuations, the long-range correlations of fluctuations in space and time. So that's what we did. I have to say also that in the so-called limit of Malthusian flux, where you actually make the density a fast field, then these results of 95 are reproduced, they hold, and the exact results in 2D for this Malthusian flux are still there. Okay, so anyway, we wanted to see what was the important of the neglected vertices, important terms in the scaling, and check the general framework for scaling, which had been done in 95, 98, but with much more powerful numerical means, you could do it much more nicely. So first of all, in the Vicsek model, if you're very naive and you measure the global polar order parameter, this is the average polarity of particles, normalize the modulus of it, and it goes from 0 to 1. So these are really ordered phase. At fixed parameters and your very system size, you see that the order parameter decreases with system size, but slower than a power law, which is this is a log-log scale, log-log plot. And you can fit these points very nicely to, I'm going to an asymptotic finite value here, pi infinity. And I go to this finite value, which in some sense proves numerically long-range order in an algebraic manner. This is actually a measure of one of the exponents, and I have no time to discuss this. But you can also look at I'll come back here, you can also look at the objects of interest in the Toner 2 theory, the two-point correlation functions of fluctuations of density and fluctuations of velocity, transverse velocity, and measure exponents. So I don't show you any of these results. It's actually very hard because there is a pre-asymptotic regime. Even if we change parameters, we cannot really reduce this regime much. And these are results of simulations involving up to 100 million particles for some of them. And I just want to show you the difference between the Toner 295 used to be exact, still exact for Malthusian flux numbers for these exponents and the ones we measure. And some differences are pretty big, so which means that these neglected vertices indeed do carry some importance. But the general qualitative structure unraveled, discovered by Toner and Tu is of course valid, which is very nice. Now the anisotropy exponent, which was something that people in animal behavior in particular are interested in, correlations decay with different exponent in the transverse and the longitudinal direction compared to the mean center of mass motion. This was predicted to be initially rather, 1 is isotropic, so 0.6 is rather strongly anisotropic. And we measure something which we finally concluded to be smaller than 1 in 2D, but hardly. And in 3D we cannot say. So there's very weak anisotropy. Okay, that's for the specialists. I skip the rest. I see time running. So I will now switch to, so that's for the quantitative assessment of the Toner 2 theory. It's qualitatively valid and quantitatively very large differences in exponents in 2 dimensions with the predicted ones predicted in this restricted setting of 95. Now for the nematic case, so now we have the 2 classes, DADAM classes with nematic alignment. So one is active nematics, where the particles do these velocity reversals at some finite rate, here a fast rate in fact. And the other one is the Vicsek rods, where the particles do not reverse velocity but align nematically. Okay, so it's been known for a long time that active nematics shows quasi-long-range order with continuously varying exponents. So here again, here you have a nematic global order parameter, scalar, it's norm at least, as a function of system size in log-log scales for different noise values here. For very low noise, it's basically a very, very small exponent. These are still very small exponents anyway, and you see that the exponent, the slope is getting larger as you go down here, as you increase the noise. And the slope actually goes like the variance of the noise, which is similar to the XY model. And so this concludes numerically to quasi-long-range nematic order in active nematics, in Vicsek-style dry active nematics. And this is indeed what all theoretical approaches are predicting. The problem is that these theoretical approaches, mostly by Ramaswamy and Sriram Ramaswamy and co-workers, they all predict quasi-long-range order in whatever the particle's motion is, so including in the so-called Rods case, where there are no velocity reversals. And in fact, a fairly large scale, at least at the time, simulations in this case, this is again the global nematic order parameter versus, system size in log-log scales. And you see that again, like before the Vicsek model, this goes slower than a power law. And this is very well fitted like an algebraic decay to some finite asymptotic value. So these numerical results at the time if you extrapolate them, bravely, you conclude to true long-range nematic order. And that has been a problem within this little world of, DADAM systems and Vicsek style things. So recently we came back to this, and the result is of these, newer, better simulations, and maybe better parameters chosen to do this, is that in fact, so look at the middle panel here. Again, this is S versus L in log-log. You see that indeed here you have something growing slower than a parallel. There's a bit of curvature, but after this length scale, and I'll come back to this in a minute, this goes into a nice quasi-long range order decay with a constant slope, which is very small but significant. Okay, so that is evidence for us that beyond a given length scale, you do have in fact quasi-long range order. So this length scale is what? This length scale is the typical length scale over which particles travel. You have a nematic, global nematic state. So half of the particles roughly going, say, left to right, and the other half going right to left. And if I follow one particle, say, belonging to the left-going subpopulation for now, it will turn around, even though it has no intrinsic velocity reversal, it will turn around due to fluctuations and collisions, and join the right-going population. And it does this at a finite rate. It's really the flight times of the flight paths, the flight lengths along one, when you belong to one of the two subpopulations, are distributed exponentially, defining a very well-defined mean characteristic time or characteristic length scale LR, R like reversal. So these reversals are not imposed, they are observed. And this is easy to measure. This is actually rather quickly system size independent. So it's a well-defined length scale. And here it is right here. So it is really at the crossover between pre-asymptotic true long-range order-like decay that you see here, and the post-asymptotic behavior quasi-long-range order. So conclusion of this numerical results is that there are no two different nematic classes. Asymptotically, if you can afford it, numerically or experimentally, you should always see quasi-long-range order. So everybody should be happy on the theory side. Now, nevertheless, this LR scale, as I show here on the left panel, this is as a function of a noise or inverse of noise amplitude, noise strength here, quickly diverges. Here this goes like noise strength to the power -8. So if you decrease the noise, this really reaches very, very easily astronomical values. Okay. Now, if you put yourself in numerical conditions such that this LR scale is way beyond what you can ever simulate, you basically have a de facto infinite range of scales over which to observe a pre-asymptotic behavior. And this pre-asymptotic behavior, if you look at the right panel here, numerically again, is this L is normalized by LR here. So we are still, it goes, well, still anyway, much smaller than LR. And you see that you go from a pre-asymptotic finite decay of the slope, which means a true long-range order behavior here, and you cross over at some other crossover scale to the more asymptotic, so to speak, again, straight here behavior, which also concludes, this means also true long-range nematic order. Okay, so now these are numerical facts, and we wanted to have possibly a theoretical understanding of this. And so what we did is we have a theory for this regime, for when whatever length scale you're interested in particular system size, is much, much smaller than this reversal length scale LR, which we know can be astronomically large. Okay, so we give up the traditional representation for active nematics and active nematics theories, and now we consider two subpopulations, the two that I mentioned before, the L and the R subpopulation, from the start. These two populations are each exchanging members explicitly at a rate to R, which, if you want, is 1/LR up to some speed. And they do, so particles there in these two populations, within a population, a given subpopulation, the particle do ferromagnetic alignment. So all the left going particles, or the L particles, if you want, align ferromagnetically, whether they are actually in an ordered phase or not, doesn't matter, that's a rule. But a L and an R particle will actually anti-align whatever their orientations and whatever the global state of the system. So we have alignment within each group, but anti-alignment between particles belonging to the two different groups. And now, of course, for low enough noise, there is an ordered phase, a nematically ordered phase in this system. And so what we did is basically not simulate this thing, but just write down a theory and study its scaling structure. So we write two coupled Boltzmann equations for the two one-body probability functions of the two populations L and R. So this is the equation for FL. The one for FR is a classic thing. For those of you who know Boltzmann equations, it should look like a Boltzmann equation. This is the exchange term here in the middle. Okay, and there's a symmetric was a similar equation for FR, where you exchange the R and L labels here. And we apply what we call among ourselves the Boltzmann-Ginzburg-Landau method to derive systematically hydrodynamic equations for the first modes of F, which is the sum of FR and FL, and G, which is the difference. And what you see immediately if you do this is that the only field that can produce order, so that has a linear coefficient that can change sign, is the G1 field, which is the difference between the polar component of the R population and the polar component of the L populations. They're going in opposite directions. And also this is in some sense morally akin to the nematic field, although it's not explicitly the usual nematic field. So that's the one governing constant. So we do our machinery, we arrive at equations for these four fields. This is the total density, that's just a conservation. This is written in our favorite complex notation, which I have no time to explain. What I want you to see here is that G1 is the important field. The G1 equation is very much like the Toner 2 equation. Specialists will see that some small differences, and of course it's coupled to F1 via these terms here. So you have, this is a result of some systematic procedure. This has the structure of two coupled Toner 2 systems, rho G1 and G0 G1 and rho F1. But anyway, so, and then we performed the same calculations that Toner and 2 did, so to speak, in 95 and other people since also. So we do some kind of analysis of fluctuations around the ordered solution at linear level. That gives the expressions that are sort of in too small script here for you to read, and it's not very important, but for fluctuations of the density field, of the transverse G1 field, and the G0 field, which is also hydrodynamic in the large LR limit. And here this has a denominator which signals peaks in the frequency spectra. And this structure is similar to Toner 2. It has three peaks, one diffusive peak and two propagative peaks, but these propagative peaks are actually symmetric with respect to 0. Okay, so we have a structure of scaling of fluctuations similar to Toner 2, but qualitatively not, well, yeah, generally speaking, but qualitatively different, in fact. We also have nonlinear arguments at the RG, nonlinear arguments predicting that the same general scaling structure as Toner 2 theory should hold. And we did not do any true RG calculation at the nonlinear level. Actually, neither did Toner and 2, but we did numerics, high quality numerics, I would say. And these high quality numerics here, I show you some results. First, you do have indeed 3 peaks in the frequency spectrum of here order fluctuations. So these are simulations of the original Vicsek rods model and not the a priori 2 population model from which the theory was derived. So you see 3 peaks, 1 centered peak and 2 symmetric peaks. These symmetric propagative peaks, they vary with a wave number linearly you can measure sound speeds, and these sound speeds measured here in red dots fall perfectly onto the predicted behavior in underlying dashed line here. This is the polar plots of these sound speeds. For those of you who know this over Toner 2 theory, this is very different. And we can measure scaling. Again, there's an intermediate pre-asymptotic scaling region, but past that, we have indeed scaling behavior just like in Toner 2 with different exponent. And one peculiarity is that the anisotropy exponent is actually larger than 1 here, whereas in Toner 2 polar case, it is smaller than 1. It's a kind of oppositely anisotropic scaling. Okay, so we're very happy. We have a theory. Its predictions are verified very nicely. And that, of course, this theory, I forgot to mention the key point, you know, the value of exponents and other signatures here prove, well, these are numerical proofs, but they are in agreement with theoretical arguments that you have true long-range nematic order in this case. So for the real system, this is only true up to this scale LR, but this scale can be very, very large. And we can account for this pre-asymptotic, very large region of parameter space, so to speak, or scale space, by this theory predicting true long-range nematic order. So to that extent, you can indeed have true long-range nematic order, not just quasi-long-range nematic order in active matter, in you know, nematic Vicsek starred systems. And, okay, so these are summaries. True long-range order is very generic, even in nematic case, even though asymptotically it's quasi-long-range and there's only one class. So then Toner 2 theory is qualitatively okay, but some serious RG should be done one day to get other results than just numerics for the scaling exponents and other things, details if you want. Okay, now there's an experimental confirmation of this new nematic theory that is pending, and I have 0 minutes, so I will flash at you what you saw at the very beginning here. What you see, in fact, is elongated E. coli bacteria swimming very, very constrained between two glass plates. So they're really touching the two glass plates almost constantly. And if you are dense enough number, you have enough bacteria, it's dense enough system, then you see, I'm going to run it again probably if I can. You should see with a good eye that there's a large scale. This is a millimeter by millimeter snapshot. There is nematic order along the diagonal here. If you see it, it's good for you. If you don't see it, it's not. So now Daiki Nishiguchi, who did these experiments, is reprocessing his data, trying to measure in particular the sound speeds and other things that we have predicted for this new theory for the nematic long-range ordered state. But what he did in the past is to show that the nematic order, which is shown here in the middle, in a log-log scale versus system size in log-log scales, goes slower than a parallel, and again, very well fitted to going to an asymptotic finite value as a parallel, which we take as a signature of true long-range nematic order, or we took at the time. Okay. All right, that's it. Thank you for your attention, for being here, so to speak, you know, wherever you are.
Thank you very much, Hugues. I really enjoyed your talk and all these different beautiful cases that you showed. So it's time for questions. You can raise your hand. Let me check here if there is any one ready to ask. It was too clear.
There's Yuhai, of course, you know.
So in which direction are you moving now in this?
Yuhai has his hands.
Oh, Yuhai is there? I don't
Yeah,
see.
yeah.
Ah, okay. So Yuhai, yeah, sure. I didn't see it in the panelist.
Short of John Toner, you know, who could.
Sure.
No. This is fascinating. Thanks for a wonderful talk. You probably, as you know, that I haven't been kept up with this recent literature myself, but this is pretty nice. And so technical question is, I still remember the days we plowing through hundreds of Feynman diagrams, trying to find high order corrections, and we couldn't. And the conclusion was that we tried hard enough, so therefore there isn't. So apparently this is wrong. But on the other hand, I think the fact that the critical dimension is 4 and we can follow this RG, we're not missing any relevant variable, in the sense that if you just follow the RG and take into account all the relevant terms, seems like you're suggesting if somebody really do that hard work, to count for all the relevant terms, you would be able to account for the different exponent that we got by just simply stop at the first order and
the very fact that the Malthusian version, which gets rid of a density field, and the density field, for that problem of long range order is not so important. It's crucial for the phase separation business, but it's not really for the long range order. So you get rid of the density field, make it a fast field, and then your initial calculation is still valid at all orders in perturbation theory, which is still not a full proof for me that there's no other non-perturbative anything going on. But so, you have this, so this is still holding, that's fine. And then the structure of a theory is strengthened by this and numerical results. And who cares about the exact values of the exponents? You may wonder why the anisotropy exponent is so close to 1 that you cannot rule out that it's 1 actually.
So that's my last
only nagging thing. One other thing, conclusion from the numerics is that we see that the hyperscaling relationship between Z dynamical exponent and some combination of a static exponents holds, which we call zeta, is holds, and this means that the additive noise amplitude terms or coefficients are not renormalized, and so that additive noise is the right thing to do, in fact, which was also a problem raised by the number of people, including me, in the past. If you have, or even if you don't have additive noise, it will be generated and it will dominate. So it's fine to put additive noise. So, it's pretty good. It's just values of exponents, and maybe why is it that anisotropy is so weak?
Yeah, so that's my next question, is that do you see any reason, if you just assume for some reason the system is isotropic in the asymptotic limit, would that help you to get other exponent correct? I mean, would that allow you to do that? I mean, it's just,
well, in some sense, you could do with one less measurement, indeed. But I don't think I don't see how to associate this with, because it's still, if you're at the linear level, it's quasi-long range order, as you know, and the linear level exponents are, it's isotropic scaling and all that. And so at the nonlinear level, this carries over under the flow, and whether that means some deeper symmetry, not too clear to me. And,
right. I mean, just technically, I mean, when we did the numerical simulation, which is by far much less than the system size you have done, the way we sort of enforce the orientational order in the not let the overall velocity meandering, right? Over a long time, it will meander. So I wonder whether that could be a problem. I mean,
in these new simulations, the ones that are published, most of them are with a wall also.
With a wall, okay. So that's
we were very careful. We threw out, at least 1/2, maybe 3/4 of the system. And for very large sizes, but not the largest, we did compare the 3 possible ways. Either you impose an external field, or you just rotate your solution with to analyze fluctuations with the current global direction, and they all give the same thing. I now believe that imposing a field is better, but of course you have to run several fields values to ensure every time that you are in the linear response regime. Okay, so you multiply, you lose a factor 2 or 3 here, but then because you keep the whole space-time domain, it compensates for what you have to throw out when you take walls. So most of the results I've shown are actually with walls, like you did. I'm not sure you threw out most. Anyway, what we see mostly is that there's a pre-asymptotic regime, which means that and typically this length scale is around a few hundred interaction lengths. So you have the right scaling structure below that crossover scale, but these are not the right exponents. And only after that you
I see.
you cross over to what is hopefully the asymptotic behavior, of course, numerically, you know, so that's all you can do. So yeah, so we do, I don't think that's the, you know, the numerics are the way we did the numerics, or you did. It's just a matter of basically system sizes and time scales also, because of course the time scales.
Okay, good, thank you.
Yeah.
Oh, no, now it's working. Can you hear? Yeah.
Yes.
No, I was just going to ask you before finishing, in what direction are you moving in this multidimensional cube that you put?
Well, you know, I have exciting work on bacteria. I mean, real bacteria, and of course, I don't do the experiments.
Sure.
These are Chinese bacteria, and exciting stuff that we are working on right now. And so this is a best of both worlds. You know, bacteria should be important to everybody, and they are real system. You can look at millions of them rather easily, and they can do all kinds of things that physicists are thinking about, and even things that we haven't thought about before, which is even more exciting. So that's one part. On the theory side, we have actually some new surprises for the Vicsek model, but I won't talk about this now. Yes. So, you know, 7 years later now, there are still some very surprising things. And of course, we discover these on huge systems compared to, you know, what people looked at in 95. You know. Let's say if you take, you know, hundreds of millions of particles, I guarantee you can see some fascinating stuff that nobody has seen before, which makes you think. So right now we are there, and of course, these numerics are heavy by today's standards, but they do reveal qualitatively new things. Even there, you know, even in the most studied model of the world, still some surprises. Yeah.
Okay, quite amazing. So thank you again, Hugues.
You're welcome.
Talk, and looking forward to see you soon.